So I'll go ahead and get started. Um, so my name is Matthew Gillespie. Hopefully my audio is all good. Um, but I am a fourth year PhD student from Arizona State University, and I'm going to be talking about cross products and group C-star algebras and how these things are kind of related to each other, one being kind of a special case of the other. Because this topic is so vast, I'm hoping to take a bird's eye perspective and kind of what I really want to get across in this talk is the universality of these objects and from their full variance. They also have reduced variance of cross products, and we'll talk about those as well. But I really just want to get across kind of the main idea of what these objects do and why they're so useful. And so it'll be a very, very high level perspective of what's going on here. So to kind of motivate a little bit about what's going on, let's go ahead and look at some basic example, a classical problem in dynamical systems. So, and of course, feel free to stop me if any of you have any questions about notation or what any of these objects are. So for our motivation, I'm going to let X be a locally compact Hausdorff source space, and I'm going to let phi be a homeomorphism of X. So right, by Gelfand duality, this is something you've likely seen in the lecture so far. Right, there's a naturally associated C-star algebra 2X, which is the C0 functions on X itself. So it turns out, right, that the integers will act naturally on C0 of X in a very natural way, and that's by simply iterating the homeomorphism phi. So to say that formally, what's going on there? Right, so formally there is a group homomorphism alpha from the integers to the automorphism group of the C0 functions that takes an integer n and sends it to alpha sub n. And alpha sub n is an automorphism of C0, and so I apply it to a function that gives me another function on C0, and when I evaluate that at X, that is given by the rule, which is f applied to phi to the n of X. That is, I take X, I apply phi to it n times, and then I apply f to that. So for positive integers, right, I'm simply just applying phi that many times. But for negative integers, right, I'm applying the inverse of phi that many times, if that makes sense. So we can summarize the data here by this triple. So the triple is the C-star algebra C0 of X, the group, which is the integers, and the action, which is the homomorphism alpha. So studying this system is extremely similar to studying just a very classical problem in topological dynamics. So all that's happening here is for topological dynamics, I would have just the space X. I would have the group action, so I have the group, and then I would have the group action here. Only difference is I'm replacing the topological space with its closest relative in the C-star algebraic sense, which is C0 of X. So this is basically just a problem in classical dynamics. And as I said, C0 of X is a C-star algebra. So, and we're talking about C-star algebras. So the question here is there some clever way to define a new C-star algebra that will conglomerate all of the data here? So I have my C-star algebra C0, I have the group of integers, and I have the homomorphism alpha. So is there some way that I can build a C-star algebra out of these three things that somehow allows me to study this classical system using C-star algebraic techniques? And the reason we want to do that is because, well, first of all, C-star algebras, as you've probably seen by now, have many useful properties and have very nice kind of magical things that can occur in them, and which is very nice. And so studying a more complicated problem, like a topological dynamics problem, in that context would be very useful to answering questions about those things. But moreover, right, if we can somehow take data like this in general, where I have a C-star algebra group and an action, and make a new C-star algebra out of it, that potentially gives us a massive class now of C-star algebras that we can study. And so this should give hopefully a little bit of motivation as to where this construction will come from. So before I get into that, I need to talk a little bit about representation theory of C-star algebras. Some of you may have seen this before, maybe not quite in this context or how this is framed, but this is like kind of the most abstract way that we can talk about representations. And I need to talk about the multiplier algebra and the topology that comes along with the multiplier algebra that we usually use. So first we let A and B be C-star algebras. So I want to recall, and this will be a theme throughout this talk, and something that I really want you guys to take away from this is that many of these objects, many C-star algebras at the high level of research, these are studied in terms of the universal properties they satisfy, not necessarily what the objects themselves contain. And I think that was a very hard hurdle for me personally when I was a first year, second year student in studying these objects, is that I was trying to think of them as like these very concrete things all the time, but a lot of the times they're much more useful when you just think about them in terms of a property they satisfy. So in this case, you've probably have seen maybe the multiplier algebra as like, the collection of double centralizers of a C-star algebra. But instead, we can just think about the multiplier algebra as just the C-star algebra, which is universal, right, in the sense that it is the largest unital C-star algebra containing B in this case as an essential ideal. So the most common example is that the multiplier algebra of the compact operators on Hilbert space is the bounded operators. And there's a very natural topology that, other than the norm topology, that we can put on the multiplier algebra, which is very, very useful. And this is called the strict topology. So the strict topology is a semi-norm topology, so it's just the initial topology that's induced by a family of semi-norms, which I'm denoting by this little b on the left with rho, or rho sub b is on the right. These are semi-norms defined in the following way. So what they do is, with b on the left sub rho, it takes a multiplier and it sends it to the norm of b times m. So I'm multiplying by b on the left, and that's what this little b here is on the left to indicate that. And then rho sub b does the exact same thing, except I'm multiplying by b on the right. And so since this is the initial topology, that is the weakest topology making these maps continuous, convergence of a net of multipliers in this topology simply means that I have to have m sub I times b, that is right multiplication and left multiplication by elements of the C-star algebra B. These nets have to now converge in norm in the C-star algebra B, right? Because when I multiply one of these multipliers by an element of B, it has to land back in B, because B, right, is an essential ideal of its multiplier algebra. So this is a very common topology that'll be used a lot, and the reason we care about this will be kind of relevant in the next slide, but moving on. So a star homomorphism of pi from A to multipliers of B, we call this non-degenerate, provided that this collection, which is the closed span of all of the products of elements from pi of A times B, this gives you back the whole C-star algebra B itself. This is just a definition, but there is a very useful non-trivial theorem that I highly recommend, if you haven't seen it before, to Google it. It's a very, very useful theorem in functional analysis, which actually simplifies this non-degeneracy condition. So that's called the Cohen-Hewitt factorization theorem. And it turns out by this theorem in functional analysis, the above condition, which is that the closed span of all of these products recovering the whole C-star algebra B, this is exactly the same thing as just the set of all products of elements from pi of A times B giving you back all of B. And so what this means is that I can give it any element of my C-star algebra B, and where I have a non-degenerate representation, I can actually factor every element of B as a product of two elements. So if I have given any B, this will be embarrassing with my handwriting. So given any B and B, what this is really saying then is that I can actually write B as a factorization. So I have pi of some A times some B prime. And so for some examples of C-star algebras, this may be obvious that you can do something like this, but in general, right, factoring elements of a C-star algebra is a highly non-trivial thing. And so this is I highly recommend Googling this theorem. It's very, very useful and very fascinating. It's actually also stated in a much higher generality than what I'm doing here. Anyway, so let's see here, clear. All right. So with those definitions out of the way, if there's no questions, I will move on to the next slide. This is again relating more back to the strict topology, and these are some exercises that on the next slide that I hope you guys can write down maybe and like solve on your own time. It's very useful. So related to the material we just saw, this is why the multiplier algebra and the strict topology, these are so useful together. So it turns out that B is always strictly dense in its multiplier algebra. So that is, the strict completion of B is always M of B. And that's one of the main reasons why this is so useful, because we can always just realize now M of B as just the strict completion of B. And moreover, every non-degenerate star homomorphism, pi from A to multipliers of B, is strictly continuous. So in particular, because, right, in this case, if A is strictly dense in its multiplier algebra M of A, that means that I'll be able to always find a unique extension to the multipliers of A, such that the extension is also a star homomorphism. And this, again, this is a very, very useful fact, and honestly, it's so useful in the theory of C-star algebras that it's not even usually mentioned by name. And so if you haven't seen this before, if you've read any papers related to C-star algebras or maybe some more advanced texts, people will just extend non-degenerate star homomorphisms to multiplier algebras, and they won't even say what they're doing. But this is a very good exercise to verify that this is true and how this works. And so I highly recommend trying these out. The key to solving these two problems is to consider approximate units of the base algebra. So in particular, just as an example, right, to tackle the first one here, where B is strictly dense in M of B, I would first consider something like a approximate unit, E sub lambda in B, and I would first verify that E lambda converges to the unit in M of B strictly. That should be relatively simple based upon the definition of what an approximate unit does. And that should hopefully get you started on this problem. But this isn't too hard to see that this is true. And then you want to do a very similar thing in part B, and then use this non-degeneracy condition to verify that you can always extend homomorphisms of this form to multiplier algebras. Any questions so far? Okay, perfect. So with some of that representation theory out of the way, we can now go back to the main material that we're trying to get through. So, right, as we saw in the first slide, we can kind of generalize the concept of this triple, where I have a C-star algebra, a group, and some group action on the C-star algebra by automorphisms. So in general, we call this a C-star dynamical system, and it'll consist, again, like I said, of a C-star algebra A locally compact Hausdorff group G, and a homomorphism alpha from G, again, to automorphisms of A. So this is just a group action on A by automorphisms, and we stipulate that this homomorphism is continuous in the point norm topology on the automorphism group of A. So what that means is that if I have a net SI converging to S and G, that simply means that if I plug in S of I to alpha and evaluate this at any point in A, that this net will converge in norm on A. And that's for every single element, A, little a, and big A. And as I said, right, our original example where I had C0 of x, the integers, and alpha, right, this triple will satisfy these conditions. And, right, to study these C-star dynamical systems, right, all of the relevant information of these, just like in most concepts you'll see in graduate school and beyond, is that in order to study an abstract mathematical object, it's usually best to study its representation theory to get a handle on what the object really is and how it behaves. In this case, there are also representation theory associated to these C-star dynamical systems. That's a kind of a vague term, right? Because we have three different things here. We have a C-star algebra and a group and an action. So our representation theory ought to encapsulate all three of those things. And we also want to restrict our attention to a manageable class of representations of this system. So I'm going to introduce what's called a covariant homomorphism, and or less generally, covariant representations of this system. So given this data A, G, and alpha, a covariant homomorphism of this system on any C-star algebra B is a pair, so pi and u. Now, pi in this case is a non-degenerate star homomorphism of A into, again, multipliers of the C-star algebra B. And u, which this is a typo, this should be a lowercase u. U is a strictly continuous unitary representation of G. So what that means is that I have a continuous function in the strict topology. So what I mean really by that is that if I have, S of I converging to S and G, then U of Si will converge to U of S strictly in the multiplier algebra. So this is a strictly continuous function that's unitary valued. So U takes the value of unitaries in the multiplier algebra of B. And it's also a group homomorphism, right? So that's what U is. And this paired pi and U satisfies the following covariance condition, which is that the following equation holds. So this may look kind of random, but I'll explain why this is a very important condition. But the condition simply just says that pi of alpha sub s of A looks like U of S pi of A U of S star. So again, U of S is a unitary, and so all I'm doing here is on the right-hand side is conjugating pi of A by the unitary U of S. And I need this to hold for all elements S in the group and all elements A in the C-star algebra. Now, the reason why this condition is useful is because the covariance condition is taking the action alpha and it's making it look inner. So what do I mean by this? If we go back to this condition here, alpha is simply just any group homomorphism, right, of G into the automorphism group of A. So there's a very, very massive range of things that alpha could be. If you know anything about automorphism groups of C-star algebras, you know that they're extremely large and very general, and there's a whole book called C-star algebras and their automorphism groups, which is like a 700-page volume, so it's very, very, very vast subject of study. So in particular, the action alpha is potentially very unwieldy in what it is, and what a covariant representation is doing, or a covariant homomorphism, what it's doing is the following, right? Alpha, when I apply pi to it, in the image pi of A, so because we're applying pi to this thing, what it looks like in the image pi of A is simply just a unitary conjugation, right? That's really what this equation is saying. So when I say that this makes alpha look inner in pi of a, that means I'm saying it makes it look like a unitary conjugation in the image. And these are particularly the representations that we're going to care about. So all of the representations that make the action alpha of the system look like a unitary conjugation. So with that being said, we could finally talk about what a cross-product C-star algebra is. So again, we're going to have a fixed C-star dynamical system. If you may have read a little bit about cross products, maybe in the goals notes, and these will be introduced in a much less general framework from what I remember, at least, which is that usually you have a discrete group G, and they define, I believe they define the reduced cross product only. Perhaps this has changed since I've taken goals, but they basically define it as, you know, this closed span of sums of these unitaries that you're getting from this convolution algebra, and you're looking at this this closure inside of B of L2 under this this left regular representation. I'm going to talk about a much more general construction, which will encapsulate the construction you'll probably see in the goals notes, and that's the full cross product. The full cross product has a very nice universal property. So what is it? Well, the cross product of this system is a C-star algebra, which we're going to denote by A with this R times symbol and then alpha of G. So the way that you can kind of say this is A cross G, or A cross of alpha G if the action alpha is, you need to specify that. So the cross product is a C-star algebra, A cross G, and together with a covariant pair of homomorphisms, so in this case, I sub A, which is a faithful, even though I didn't write that here, it's not very necessary, but I sub A is faithful, and these are both together a covariant homomorphism of A and G into the multipliers of this C-star algebra. Throughout, I noticed that I have this typo where I don't have this symbol properly written on some of these cross products, but there should always be another bar right here. So if you only see the time symbol like this, I do mean this. I just there's typos throughout this. Right. So the cross product again is this C-star algebra A cross G, and together with this covariant pair I sub A and I sub G, and this triple of data satisfies the following universal property. So for any covariant homomorphism pi and u on a C-star algebra B, there exists a unique non-degenerate star homomorphism pi cross u, which is called the integrated form of the covariant homomorphism, such that the following diagram commutes. Right, so this is the universal property of what a cross product is, a full cross product. I kind of want to break down, of course, what this is, because this is a very complicated looking construction. Lots of things going on here. So to kind of break down what this is saying, and I'll refer back to this commutative diagram on the next slide. First of all, I want to mention that this construction that I defined here, I'm basically just, without any proof, I'm saying that this thing always exists, because I'm saying the cross product of this system is this thing, this C-star algebra A cross G. First of all, right, we need to actually show that such a construction always exists for the universal property to make any sense. So that's not trivial, and that's not clear from what I'm saying here. So suspend disbelief for a moment. But I want to break down what this universal property really is saying. So given a covariant homomorphism, so pi and u of the system, what is the universal property doing? Well, if we go back, the universal property says, if I take one of these things, so I take a pi and u, the universal property of this C-star algebra A cross G, it spits out a unique non-degenerate star homomorphism of the cross product, and satisfying this property. So in particular, we have a mapping or a rule that takes a covariant homomorphism and sends it to its unique this unique output, which is the integrated form of this representation pair. Now, on the other hand, if I have any non-degenerate star homomorphism of the cross product into some C-star algebra B, then you can check if I compose phi with I sub A and I compose phi with I sub G, that this actually gives you a covariant homomorphism of A, G, and alpha. So, in other words, I have a mapping that takes a representation of the cross product and sends it to a covariant pair of this system. So together then, what do we have? Well, I have a map that takes a covariant homomorphism of the system and it sends it to a representation of the cross product. And on the other hand, given any representation of the cross product, I get a covariant homomorphism of the system, right? So in other words, what that means is we have a bijective correspondence, again, by the uniqueness of this integrated form, we have a bijective correspondence between the covariant representation theory of the system AG alpha and the non-degenerate representation theory of the C-star algebra, which is A cross G. So what we're actually doing, right, we're taking all of the relevant representation theory, that is all of the relevant information we care about in this system, this dynamical system, and we're translating it into the representation theory, all of the relevant, when I say relevant, I mean the non-degenerate, representation theory of this new C-star algebra. So in other words, if I want to study this object, the dynamical system, and all of its relevant information through covariant homomorphisms, I can instead simply study the representation theory of this C-star algebra, and then I can use now a bunch of C-star algebraic techniques applied to this new thing to circumvent having to study this more complicated triple of things, A, G, and alpha. So to kind of reiterate what I just said, right, all of the relevant information of the system AG alpha, it's captured by all of the relevant representations of the associated cross product C-star algebra, which is A cross G. Are there any questions about this construction? I know this is a lot of information. Okay. So I didn't talk about this first bullet point, which is existence. So to get existence of the cross product, we need to talk about some topics that you probably haven't seen in these lecture notes, at least in this generality. So it's okay if you don't quite understand what's going on here, because the proof of existence, again, when I was taking goals and I was going through this material, and also in my first and second year of my PhD, learning about this stuff, I always thought about cross products. I always thought of them as this particular construction that is shown in the existence proof. But it's actually, again, like I said, infinitely nicer to think again of the cross product not as this construction I'm about to show you that is this concrete thing, but more so again in terms of a C-star algebra which satisfies a nice universal property. But nonetheless, we'll go through how to actually construct this object. So first of all, we're going to start with the data A, G, and alpha. Now delta here is the modular function of G, and mu is the left hard measure. So if you don't know what the modular function of a locally compact group is, basically it's how you translate between the left and right hard measure. So if I want to do a change in variables between left and right hard measure and integration, I use this homomorphism delta. If that's confusing, you can think of just G as a discrete group, so you don't have to worry about this, and mu is counting measure. So what we're going to be doing is we're going to place we're going to start with the vector space, which is the continuous compactly supported functions from the group into the C-star algebra A. And all we're going to do is we're going to place a star algebra structure on this thing, and then a C-star norm on it, and then we're going to complete this new star algebra with respect to that norm, and that'll be our cross product. So first of all, for two continuous compactly supported functions, f and g, we're going to define a new product. So multiplication of f and g evaluated at s is this convolution. It's a twisted convolution because we're twisting it by the action alpha. If the action was trivial, this would literally just be convolution of functions, right? So in this case, all I'm doing is adding this twist by alpha. And again, why this might be confusing is because these functions are taking values in a C-star algebra, they're not scalar valued functions, right? So integrating this thing might feel weird because, right, these are not, this is called vector value integration. This is not obvious that this makes any sense. Again, if this is confused, maybe you're uncomfortable with this, you can, again, if you take G to be a discrete group and mu to be counting measure, you can replace this integral by just a sum. And then all you're doing is just adding up a bunch of products of things inside of a C-star algebra. However, if you kind of want a further explanation as to what vector value integration is, it's very similar to how you define integrals of, functions from a locally compact Hausdorff space into, bounded operators on Hilbert space, right? It's basically how you define an integral of f in that case, right, is simply that it's the unique operator that does the following. So if I apply two Hilbert space vectors in the inner product, this is characterized by the fact that this is equal to the inner product, the integral of the inner product of these vectors. So in the same way, this vector valued integral is defined in the sense that it's the unique element of the C-star algebra A, such that if I apply a bounded linear functional to it, that this is equal to the integral of the bounded linear functional applied to the stuff inside. That's all it is. Right, so that's our twisted convolution product. And I do make a mention here, it's basically how you would define like the Borel functional calculus. It's a very similar process, how you define these integrals. We also define an involution in the following way. And with this involution, given a covariant pair, so a covariant homomorphism of the system, we can define a new representation of this vector space CC of GA. And how it works is, again, I'm using vector value integration here. What's happening here is well, the formula simply states that I'm integrating pi of f of s times u of s d mu of s. But what this is actually saying is I'm taking f of s and I'm looking at f of s under pi. And what I'm doing is I'm averaging the values of the function f against the unitary u, right? That's really what's happening here. If you look at it as a sum, that's exactly what this is saying. So I'm really just averaging the values of the function f against the unitary u. And this representation that does this, we'll call this the integrated form. This is how you build this representation that you see in the universal property construction. And of course, all we're going to be doing then is defining a norm and then extending all of these objects to the completion of that thing, and that'll be our cross product. So we define the full C-star norm, the full cross product norm on this vector space of this star algebra by, I look at f, and what this is doing is I'm taking the supremum over all covariant homomorphisms of the system AG alpha. I look at the integrated form of that covariant homomorphism, I apply f to it, and then I take the norm of that thing, wherever it lands.
Sorry, what is your delta in the involution function in the first bullet point?
Yeah. So this delta here.
Yes.
Yeah. So this is just the modular function of the group. So delta is just the modular function of the group, and all the modular function does, it's this strange homomorphism that exists for locally compact groups. And basically what it does, it allows you to translate between the left and right Hart measure of the group.
Oh, okay.
Yeah.
Thank you.
Of course. And yeah, as I said, if that's weird, it's not obvious that this thing exists, this delta. It takes a little bit of work. So if it's confusing, you just think of it as a discrete group with counting measure. And
yeah, where the Haar measure becomes the counting.
Yeah.
Yeah, that makes sense.
Right. So right? We have this norm where I'm souping over all covariant homomorphisms of the system. Now, some of you may have an objection to this because, first of all, it's not obvious that this norm is even finite when I take the supremum over all of these covariant homomorphisms. Secondly, right, I'm actually not even souping over a set technically. Well, at least the thing on the right-hand side here, this is not a set in general. So the set of the collection of all of these covariant homomorphisms of a system need not be a set, and that's just because, well, I don't want to get into it, but it has to do with cardinalities and things like this. So how do we get around this? Well, you can kind of think of this as, again, we're technically souping over a bunch of numbers, right? And so even though I have maybe a possible proper class of things over here, a class of numbers, right? A class of real numbers is a set because it lives inside of a set. So there's no set theoretic issues with this definition. Also, you can check this as finite, or bounded, I should say, because it's bounded by the one norm. And the way this works is that if I look at the integral of, sorry, the norm of an integral that's operator valued like this, it always satisfies the following, which is that it's less equal to the integral of the norm of the stuff inside. So in this case, right, pi is a representation of A, so the norm of that's less equal to 1, and U is unitary, so that's equal to norm 1. So this whole thing then becomes just less equal to the integral of the norm of f of s, right? Which is exactly just the one norm of f by definition. So we have boundedness, that's all good. And then we define, right, this C-star algebra A cross G with a star algebra structure. On CC of GA, we complete it with respect to this norm, and that gives us the cross product. I'm not going to get into too much detail about like how you define I sub G and I sub A because that requires you knowing a little bit about Hilbert modules and how that works. But basically, I'll have these slides posted. But the basic idea is that you can define a bounded operator between the CC of GA functions in itself by these particular formulas here. So I sub GR of f does this thing, and I sub A, right, does this thing. These will extend because they're bounded to bounded operators of the C-star algebra A cross G. And then the idea is that you want to check that these bounded operators between this cross product are what are called adjoinable relative to the kind of canonical Hilbert module associated to any C-star algebra, in this case the cross product. I don't want to get into what this is if you haven't seen it before because it's complicated, but there's a very natural isomorphism when you talk about Hilbert modules, which is that if I have any C-star algebra B, the collection of the C-star algebra of adjoinable operators of this Hilbert module associated to B is always isomorphic to the multipliers of B. I'm not going to get into the details of why that is, but what that tells you is that these elements, I sub G of R and I sub A of A, are elements of here, that is the adjoinable operators of this Hilbert module, which implies they're multipliers. And that gives you the two maps, I sub A and I sub G. Right. So I've talked about the full cross product and that in the universal construction there. So the reduced cross product and any other cross product that you come across, because there's, again, kind of like a hierarchy of these things. You guys talked about tensor products of C-star algebras in a previous lecture, I believe. So just like there's a maximal and a minimal tensor product, there is a full and reduced cross product, and there's a whole hierarchy of a whole hierarchy of cross products sandwiched in between those two things. So given the system AG and alpha again, what I'm going to be doing to define the reduced cross product is actually just I'm going to find a particular representation of the cross product, the full cross product, and then I'm going to be taking a quotient of the full cross product by the kernel of that representation, and then I'll give me my reduced cross product. So don't worry too much about like the details about all of these representations. More so, the idea is to just think about this reduced object as the quotient of the full object. All right, so first thing here, I have a multiplication representation of C0 that's just, representation by multiplication operators. Given alpha, I am going to be defining this homomorphism of A into the continuous bounded functions of G into A. This, again, by a clever identification, this actually sits inside of the multipliers of this tensor product here. Here's the formula of how it works. Nothing special, really. Lambda is our left regular representation of the group. And with this data, what we can do is we can construct the following covariant pair. So hopefully in the tensor product lecture, they talked a little bit about tensor products of representations. Otherwise, this isn't going to make any sense. But basically, what this is saying is that you can check it. Actually, this is a very valuable exercise. So if you want to check this, please do. That this pair, so I'm looking at identity of A, tensor multiplication representation, composed with this alpha tilde, and then I'm amplifying the left regular representation, that this pair is covariant, and so I can take its integrated form by the universal property of the full cross product. This gives me a representation of the full cross product, which I'm calling lambda, capital lambda. This is called colloquially the regular representation of the cross product. There's a whole slew of regular representations of the cross product, and the way that works is, in this case, I'm actually looking at what's called the induced regular representation of this trivial representation, which is the identity representation of A. If I replace this by some representation pi, this will give me what's called the induced representation of pi, and there's a whole theory of that. But for here, we're just talking about the induced one for the identity, and we call this the regular representation. And the reduced cross product, by definition, is literally just the image of the full cross product underneath this representation lambda. And just as with group theory, right? You know that your domain mod the kernel is isomorphic to the image, right? So same thing is true for C-star algebras. That the cross product, right, is going to be this reduced cross product is this image, right? And so it's isomorphic to the thing we started with modulo the kernel of that representation. And that's the best way to think about this. Also, if you kind of just trace what's happening here with all of the representations, right? M takes, that was weird. My screen just went black. Oh, there we go. So M takes C0 of G and sends it into B of L2 of G, which is, again, from what we know, is the multiplier algebra of the compacts on L2. Alpha takes, again, things in A and sends it into the multipliers of this tensor product, A tensor C0. And lambda, again, takes things in G and sends it to, again, things in the multipliers of the compacts of L2. Another good exercise to check, right, that this map on the left-hand side here takes things from A, because we're starting at A here with alpha tilde. It sends it to things in A tensor C0, and then this map takes things in A tensor C0 and sends it to things in A tensor the compacts, because that's where M sends stuff. So the left-hand side, this will end up in the multiplier algebra of A tensor the compacts. And same thing happens here with this amplification of the regular representation of little lambda. So this C-star algebra, the reduced cross product, sits inside of this bigger C-star algebra. There's also a colloquial term for this tensor product with any C-star algebra. So in this case, A tensor, the compact operators on some Hilbert space. This is called the stabilization of A. Oh, that's embarrassing. I don't know how to spell stabilization. So what I'll do instead is just say it in words to avoid embarrassing myself. So this is called the stabilization of A, just for any general C-star algebra. And this is, again, is a very useful construction. And if you study cross products more in depth, this tensor product will come up all the time. It's a very special tensor product, and so we have a very special name for it. Right, so that's the reduced cross product, just a quotient, whoops, of the full thing. Okay, so I've talked a bunch about abstract nonsense, so let's get to some examples finally. So the most trivial example we can think of, so in this case, I take the C-star algebra A, I take the trivial group, which is just the group with the single element E, and the action I'm going to be taking is just the only action I can possibly take, right? I'm going to denote that by 1, right? So 1 just sends things from the singleton group E to automorphisms of A, right? And it does nothing to the elements of A. So this cross product, right, is isomorphic naturally to A, and so is its reduced cross product. You can just check this by looking at the convolution algebra, which is just CC of, in this case, E to A, and that's very clearly identified with A. So once you do this identification, this cross product isomorphism here is obvious. So that's one of our most basic examples. If I go on the other hand, where I make the C-star algebra trivial, so I'm looking at the complex numbers, and now I have an arbitrary group, and the identity representation, again, this just leaves the elements of the complex numbers fixed, right? Because automorphisms of C are trivial. So when I do this, the cross product of the complex numbers with this trivial action by G is denoted this way, which is C star of G. This is called the full group C-star algebra. And I'll actually work out in a moment what the universal property in this case translates to. But this is a very important construction, and it's part of the title of the talk, so we'll talk about this a little bit more in the next slide. If I look at the reduced cross product of this thing, I get what's called the reduced group C-star algebra, and that's denoted with this little small r here. So two important constructions here. If I take now two arbitrary things, so A and G, but again I have the trivial action that does nothing, then this cross product is just the maximal tensor product of A with the group C-star algebra, and its reduced cross product is the minimal tensor product of A with its reduced group C-star algebra. This is an extremely important cross product. It comes up everywhere, and it's so important, in fact, that it has a name that's named after two very important people in this field. So if I take C0 of G with the group G itself, again, G is any locally compact group, and left translation is my action, then this cross product is always isomorphic to the compacts on L2. This is called the Stone-Voigt-Neumann theorem. It's a very famous theorem, and it's used all the time in cross product theory because it's very useful. So that's one to remember. And then I'll throw in one here because you'll be talking about this tomorrow with what's called the irrational rotation algebras. But you can also realize these things as a cross product. The way this works is I take some fixed irrational number theta, and I define tau to be this action of the integers on the continuous functions on the circle. And how this works is I just take tau sub n of f, and this is equal to just f applied to z, where I'm rotating z by theta n times counterclockwise. The cross product here is what's called the irrational rotation algebra. And again, you'll see this tomorrow in detail what this is. You'll define it most likely in terms of generators and relations in a universal construction, but you could also define it this way through the cross product. Right, so I want to finally circle back in our last 10 minutes here about the group C-star algebra. This is what's most important, is these two bullet points here, and what these are, and mainly what the universal property of this guy is, because that's really what we care about. What is the universal property in this special case reduced down to? So the covariance condition of the system Let's break down what it actually means by looking at the equation. So let's take any unitary representation of G, and we're going to take, I'm going to note this by TRIV, the trivial representation of C into multipliers, which is just going to take a complex number Z and send it to Z times the unit in the multiplier algebra. So with this representation in U, we can check that, right, if I apply the identity representation, the identity action, right, to Z, that does nothing to Z, and then I apply the trivial representation to Z, that gives me just Z times 1 by above here. Now, 1 is equal to just U of S times U of S star because U is a unitary. And then, of course, Z is a complex number, so I can just move the number inside of this product here, which gives me this. But again, this is exactly equal to just the trivial representation applied to the complex number Z because it doesn't do anything. And so what is this equation here? Well, this is exactly the covariance equation, right? So in particular, this pair, right, trivial representation in U is covariant, and it's covariant for any representation of G, right? I just picked an arbitrary one, and I have this fixed representation of the complex numbers, and it turns out this pair is always covariant. So what does that actually tell us? Well, what it means is that if I take any representation of G, there's obviously, again, this is just by the universal property of the cross product, there's an associated non-degenerate star homomorphism of the cross product. In this case, the cross product is what? It's the group C star algebra. And I'm going to note this integrated form by just, mu sub U to be, because this trivial part here is really irrelevant. We really care about just the U here. So this gives us a homomorphism of C star of G. Now, on the other hand, right, if I take any non-degenerate star homomorphism of the group C star algebra, by the universal property, again, just by the universal property of the cross product, if I compose this representation with I sub G, right, by our universal property, that gives us a representation of the group, which we're going to call U. So in other words, what actually happened here, well, that means that I have a bijective correspondence now between just the literal unitary representations of G and the star homomorphisms of this C star algebra. So in other words, right, the unitary representation theory of the group is literally just the non-degenerate representation theory of this C star algebra, C star of G. And that's why the group C star algebra is so useful, because if I want to study a group in any high level, I want to study its representation theory. And if I want to study its representation theory, that's complicated. It's a huge, enormous subject. I can instead reduce that to studying the C star algebra associated to it and its representation theory. And again, as we know, C star algebras in general are much more, much easier, at least on paper. These are much easier to deal with than just arbitrary groups, right? Because groups are extremely general. They're extremely unwieldy in many cases. So reducing a problem about group theory to a problem about C star algebras is very useful. And remove these. Before I go to the last slide here in the last couple of minutes, are there any questions about any of this? Okay. So again, the main takeaway of this lecture I want is that the full cross product, right, in general, is simply, so our cross product A cross G, right, this is universal for covariant representations of a dynamical system, A, G, and alpha. So it takes the representation theory of this object and moves it to representation theory of this object, which this object's much nicer because it's a C star algebra. By a special case of this more general thing here, if I look at C star of G, right, which is this trivial cross product, right, this again has the above property, but the above property here just reduces to just saying the unitary representation theory of just the group G itself. So to study this system, I want to study this system instead, right, by its representations. And if I want to study representations of the group and any operated algebraic context, I can instead just study this C-star algebra C-star of G, and it'll give me the same thing. So that's, again, the main takeaway of this lecture. I want to end in the last couple of minutes here with just some interesting further reading in this subject, because I study this subject. It is part of my my research. So some stuff that you can further read about with cross products. First thing I have here is coactions and cross product duality. So there's a way to always dualize an action of a group. So given a group, I can, if I have an abelian group, that is, I can dualize an action and get an action of the dual group that's associated to alpha if I let my group action be denoted by alpha. I can always dualize this to get a dual action of the dual group whenever G is abelian. Now, in the case of G being not abelian, you can't do this because the dual group, which is the collection of all the continuous homomorphisms from G to the unit circle, this is no longer a group. And so there's a whole theory of what's called coactions, which allows you to dualize an action when you don't have an abelian group. And this is very closely related to cross-product duality. So a coaction in a very vague sense is just this homomorphism from A to this C-star algebra that satisfies some properties. Again, if you once you know what this is, you can kind of iterate cross-product procedure, so you can do it twice. So if I do this process twice where I'm dualizing this action, I actually get this nice isomorphism, which looks like what? It's the stabilization of A. And this is, again, where this pops up a lot. This is called cross-product duality, and in particular, this theorem is called Amai-Takai duality, named after the mathematicians that proved it. This alpha we call, in this case, is the dual coaction whenever our G is not abelian. And last thing I want to talk about here is more along the lines of what I'm studying now for my thesis, which is what are called locally compact quantum groups. So again, as I said, abelian groups satisfy Pontryagin and duality. Non-abelian groups don't, because it doesn't even make sense to talk about a dual group for them. So mathematicians a couple of decades ago really wanted to find a category of objects that would satisfy a generalized version of Pontryagin duality that would encapsulate all groups. And what they ended up settling upon was this notion of a quantum group, a locally compact quantum group in the most general context. And all this really does, what this is I take the structure of a group in the base case, and I push it all to the C-star algebra C0 of G, where this delta now is a co-multiplication. So G comes with a multiplication of the group. Delta is like the multiplication, but for C0 of G, it's called a co-multiplication. G has a unit. This is a co-unit of my quote-unquote quantum group C0 of G. G has group inversion. S is an antipode, which is like the group inversion. And G also comes with a left and right Haar measure. This is called a left Haar weight phi, which is like the left Haar weight of, or left Haar measure of my quantum group. And psi is like our right Haar measure. It's called the right Haar weight. In general, what we do is we apply the Gelfand philosophy to this, and we say, okay, I have this object that's very nicely behaved when I have C0 of G, but if I instead replace C0 of G by just some arbitrary C-star algebra A, and I kind of abstract these definitions of what these things are, what happens? Turns out in general, it's too restrictive to always have these two things here, this co-unit and antipode, and so instead we consider a quadruple of objects where I have a C-star algebra, co-multiplication, and some Haar weights. And this is what a quantum group is. And these give you a class of C-star algebras which are very interesting because they exhibit many properties that a group would, but there's no underlying group to be found. And you can also talk about cross products of these things because they're associated to groups. But with that, I'll be finished talking. And thank you guys for paying attention. Are there any questions about